Testing, testing. Okay, everything working. Okay, we're ready to go. Good afternoon. This is our last session, which we're going to cover ANOVA, and that is independent measure ANOVA. There's two different type of ANOVA, independent and repeated measure. So let's see, we're recording this. Everything looks good. So yeah, this is the last session I'm gonna cover, which is synchronous, and I activated your final exam. So please check your quizzes and make sure that you took all of them. And then again, you have 2 weeks from now until 2 weeks to take the final exam and turn in all your SPSS assignment. Good luck with all your classes, and please let me know if you have any question, any concern about anything, or I can help you in any way. So without any further delay, let's get into this chapter and finish our basic stats. Next time, hopefully next semester, when you take the advanced stats, then we're going to review what we talked about this semester, and we will pick up from what we left. That means ANOVA. Again, we're going to stop at independent measure ANOVA. And we're going to continue with the repeated measure and correlation, regression, multiple regression, chi-square, and other tested statistics. So we said that for your information, there are 3 different types of t-tests. The reason I'm showing you this is because ANOVA is really another t-test. So what's the difference? The difference is that for t-tests, we only use 1 or 2 samples or groups. But for ANOVA, we use ANOVA when we have more than 2. Your book said 2 or more, but you don't use ANOVA for 2, even though SPSS does it automatically, but you use ANOVA when you have more than 2 groups or treatments. For again, back to t-tests, just briefly, there are 3 different types of t-tests, and one is exclusively t-test, which is only single sample, and the other 2 are research designs, and we're gonna build up on them. And again, tonight we're gonna go over the independent measure design. For t-test, we had 2 groups. So for For ANOVA, we have more than two groups. And then again, we'll talk more about repeated measure designs in advanced stats. Just the analogy to look at. So you know what ANOVA is? It's just a bigger machine. It does the same thing like t-test, but it's bigger. Like, for example, again, that if you want to make one or two drinks, as opposed to one or two samples you have, you use that little cup and make those drinks. But if you want to make more than two, three, four, five, or beyond that, you need a bigger machine. So that's ANOVA. It's pretty much like t-test, and you will see. More means more of everything. That means for ANOVA, we have more degrees of freedom between and within, SS between, within. So you're going to deal with more formulas. And remember we talked about this, and we said that for two independent t-tests or more, we have to use Levene test. Levene test is just hypothesis testing, but is opposite of what we've been talking about. It means that we have to accept a null. So as you can see right there, when it says significance is 0.5, that's greater than 0.05. So we accept a null. This tells us that ANOVA is our right test statistics. And then we take the, we'll perform our ANOVA. It's like permission, like green light to do these tests. And I'll show you to you when we use SPSS in a moment for ANOVA. All right, so let's see. So the name analysis of variance, if you think about it, it deals with variance. It's the same old variance with the sigma square symbol or S square. However, ANOVA is in a class by itself. That means it has new symbols for everything, including for variance. So as you can see, the new symbol for variance is MS. And, excuse me. So what is MS? MS means it's mean of squared deviation, but mean squared for short. And that's we talked about that before. This is how we talked about it. Mean squared, variance, standard deviation, population, and then again, it's the same, except it has a different name. So we're going to talk about independent measure ANOVA as opposed to repeated measure ANOVA. These are design, these are research design, and of course you use right statistics. Like for independent measure designs for research, you use independent measure ANOVA, that's the statistics. And for repeated measure designs, research, you use repeated measure statistic or ANOVA, okay? There are a couple examples of research, because this is all about research. Again, we said ANOVA is just like t-test. That means you have one independent variable, one dependent variable. So what's the difference? The difference is your independent variable is now called factor, and your independent variable has different levels. Like for example, um, this here you can see which therapy technique is more effective for stress reduction. So, okay, what is IV? What is DV? As you can see, I color code them for you so you can easily distinguish. DV is the stress, is the variable that we measure by giving you participants the stress test. But IV is not just therapy technique. It's not just therapy. Like if it was just the effect of therapy on stress, you get one IV, one DV. That's t-test. Two. So you have two groups. One group have um, they somehow have a therapy. The other one don't. They get a pep talk. That's t-test. Two groups. One group get a therapy. The other one don't get therapy. And then after 3 months, you give them a stress test, see which group did better. That's t-test. But what if you wanted to know which therapy technique is more effective? Like you wanted to try several. In this case, we have three: cognitive therapy, behavioral therapy, and cognitive behavioral therapy, CBT. You have to have three groups or three treatment. Treatment here is therapy. So you still have one IV, but which is called factor, but you have each one of them is different therapy. So your IV has three different levels. And this is one way ANOVA because we have one IV and one DV. In ANOVA, we always have one DV. But in ANOVA, our IV always have level. That's how it distinguishes itself from t-test. Because t-test is just two groups. They get a deal or they don't. That's it. That's it. So that's the example. And the rest of them are pretty much the same. You can look at them. I color code them, follow the code, and let me know if you have any question. So let's focus on independent sample ANOVA. Again, in this case, like again, you can have multiple treatments. Let's say if you have three, so you get three different distributions. Well, Noel says that they all the same. That means back to our example, therapy techniques, Noel says there's no difference between all these therapy techniques. So after 3 months of conducting therapy, different types of therapy, one, again, behavioral, and then CBT, another. Then we give them a stress test. Noel says they all gonna score the same on a stress test. It's not gonna show that, let's say, CBT is better than others. But we, as a therapist, psychologist, mental health expert, we believe that CBT is going to do better. The group that used CBT, we use CBT to treat them, are going to do better, if that's our hypothesis. Again, but Noel says no. They're all going to do the same. As usual, Noel always says not or no difference, no change. We, alternative hypothesis or researcher, we say there are differences. And we have to prove it. Test our hypothesis to find out if provable, if we can. If not, we have to accept the null. So here's the thing when it comes to ANOVA. Since we have 3 groups or more, 4, 5, if we fail to reject the null, then it's end of the game. We have to accept the null. That means, yes, null, you're right. There's no difference between the group. But if we reject the null, meaning there are differences, now we need to know, well, where are the differences? Is it difference between CBT and cognitive therapy, or CBT and humanistic and CBT, or CBT, or it depends how many groups you have. Psychoanalytic. What are the difference? I mean, difference between which one? So for that, we have to conduct another hypothesis testing, which is called post hoc test. We take it one more step further. And there are different ways to do that, but the one we're going to use tonight is called Tukey. Tukey, and we'll talk about it when we get there. What you're looking at now is the formula for ANOVA. Just like you saw, t-test has its own formula, z-score had its own formula, and the formula for ANOVA is F equal MS between, that's what the B is, and divided by MS within, that's what W is. And then again, MS is variance. Mean square is just like variance. It is a variance. So YF is the symbol for ANOVA because it's really factorial ANOVA. But we don't say that. We rarely use the factorial ANOVA. We just say ANOVA. Because again, independent variable is called factor. So that's what factorial ANOVA, that's what it is. And F stands for ANOVA. It seems very easy, that little formula, but now you have to calculate your MS between and plug it on top, calculate MS within, plug it in bottom. And I have all of the formula, this is how you do it, in here for you. That's all formula you need, all the formulas you need for tonight. It's again on the top left side, it says F equal MSB, or between, I wrote the whole thing, between treatment, or bet treatment, or you can just write B, divided by MS with or within treatment. I color code them. If you follow the color, then you understand quicker, faster, and less confused. So whatever you see in here, if it's in red, it's related to MS between. Like, again, in order to calculate MS between, that's how you do it. MS between is sum of MS, again, it's MS is ANOVA, and MS is variance, and you know variance, sigma square, is SS divided by DF, okay? Sigma square, see, SS divided by DF. But since we're dealing with red, between, so we have to stick with SS between treatment divided by DF between. Then we need to know what is SS between. How to calculate SS between? As you can see here, you need to have a sum of t squared divided by n in bracket minus g squared over n in bracket. And that tells us, and then again, DF between treatment is k minus 1, And again, if you want to calculate K, K is degrees of freedom between plus 1. So you might say, what is K, right? Okay. And what is G? If you look at on the top right side of the screen, you see those are data. Those 4 columns are 4 groups, okay? And I will go over that research in a second. But as you can see on the very top right side, it says N is 20. Capital N is total number of participants in this research. We have 5 people in each group, so 4 groups. And group are also here called treatment groups. It's better to go by treatment instead of just group, because in repeated measure you will have the same thing, except the same group will have different treatment. So it's better to know K symbol as a treatment. Number of treatment or groups, we have 4 groups, and each group get different treatments. In this one, in the previous example, then I talk about 3 different types of therapy, so K is 3 different types of treatment. In this example, this is about preference of people watching big screen TV. So we had 4 different group of people. Have them watch 85-inch big screen TV, and after let's say 30 minutes, an hour watching, we give them a satisfaction questionnaire. On a scale of 0 to 7, we ask them how satisfied they are. And those are the data, like 9 feet. You can see the first column. The mean for that is 1. That's low. For 12 feet, like you see, M2 is 2. It's a little better. But 15 feet, M3 is 5. So that's better. It's coming high, then a higher satisfaction. And then 18 feet, again, it goes down again. M4 is 4. But again, having this data, you have to prove. We have to test our hypothesis to see if there are any statistical significance between those numbers, 1, 2, 5, 4. Yeah, they are different numbers, but do they have a statistical difference, significant difference? That's what we call. And if they do, where are they? Is the difference between group 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, or 3 and 4? That's another hypothesis testing, and we're going to use, it's called post hoc test, and we're going to use Toki. To answer that question. Toki, honestly significant. So back to our formula. This is how you calculate MS between, the red, and then the bottom MS within. So MS within, if you want to calculate that, you need to have SS within and DF within. So SS within is sum of SS. So the data that you have are, is already provided the number of participants in each group, 5, 5, 5, 5, mean for each group, SS calculated for each group, SS1, SS2, SS3, add them up, sum them up. That's your SS within. Also, instead of sum of X, we have T. T means total. So total for the first column on the 9 feet is 5. And for second column is 10, and then 25, 20. And remember, I said in ANOVA we have new symbols. because it's in a class by itself, a little different than what we've been talking about. So T here means sum of X, means total for each column. And on the very top right side, you see G. Again, N, capital N, means total number of participants. That's 20. But G, capital G, is grand total. That means you have to add up all the T, T1, T2, T3, T3, and T4. So that is 5, 10, 25, and 20. That's 60. Sum of X score is already calculated for you, and K is number of treatment, number of groups of 4. Back to the MS, once you calculate the SS within, you need DF within. There are two different ways to calculate DF within, either N minus K, with total number of participants, which is here is 20 minus K, which is 416. Or the F within total is sum of DF. They're both the same. DF within or DF within total. Two things you need to know when you're dealing with DF within, that when you're dealing with actually MS within, because you need to calculate the DF within and also calculate MS within. Well, MS within is called residual. Right there it says, MS within, residual or error variance. Also, DF within is called DF error term. So keep those in mind, because in your book, when you go and look for critical value for F, you need to know the value of DF error, which is nothing but DF within. And you have to know the DF within. Okay, so all formula you need is here. Once you calculate that, you plug them into a formula. A couple of extra things at the bottom right. Again, in order to calculate the effect size, in the past for t-test, we had D was the symbol for effect size. But now we have a new symbol. It's called eta square. It's like N at the bottom right side of the screen. Like N square is eta square, and is equal to SS between treatment, red, divided by SS total. And that is same as R square. R square is N square. And so once you calculate that, that is same as R square. And this way, you know what R square and square root of R square is R. That gives you the correlation. That's how you calculate the correlation from ANOVA. And then again, you can see from previous chapter, it says at the bottom, right? SS was sum of X square minus square of sum of X. But now we have SS is sum of X square minus, instead of sum of X, we have G square. So square is G divided by N. Also, MS was SS over DF, which is variance for population, SS over DF. But now we have MS between and within, which would be SS between over DF between, and MS within would be within. SS total, so we have two SS between and within. You add them up, you get SS total. That's one way to calculate it, or you can calculate it. They use that formula I just mentioned, sum of x squared minus g squared over n. And another way to calculate df total is n minus 1, that's uppercase N. That means total number of participants. In this study, we have 20. We have 4 groups, 5 people in each. So 20 minus 1 is 19. And df total, when you add up your df between and df within. So that's pretty much all our formula except the post hoc test. So if we reject the null, if we retain the null, that's the end of it. That means there's no difference. We couldn't prove that there are significant difference here. But if we reject the null, then we need to perform another hypothesis testing, which is called post hoc test. And I'm going to show you there are a dozen of them. When in SPSS, you can see them when we use SPSS. But the one that we use tonight is Tukey. Why Tukey? Because when your participants in each group are equal, we use Tukey, even though we can use the other ones too. And we get the same result, but this one is specifically designed when you have equal number of participants in your groups. It's called Tukey's significance, honestly significance test. And HSD is the honestly significant difference. That's what it is, equal to Q. Q is another symbol, and we have to look for critical value for it. It's on page 699. We're going to do that. And you put that in there, times the square root of ms within divided by n. So Q stands for studentized range statistics. Again, we start. So again, here are hypothesis testing. Step one. Null says no difference. All the mean for all the groups are equal. Mean 1 equal, right there is step 1, green dots. Mean 1, mu1 equal to mu2, mu3, mu4. Even Steven, no differences. But we are saying at least one of these groups is different than others. One of these treatments is going to be different than others. And then we have to find our critical cut point, same way we did for t-test. We need to know what is degrees of freedom between and within, which is called df error, and df within, and then find out. And you notice that distribution for the ANOVA is no longer symmetrical or bell-shaped. It's positively skewed. It has a tail on the right. And that tells us that the value of ANOVA will always be positive. It's not going to be less than 0. It's going to be 0 and it goes to right. So let's go over our practice. This is again all the formula that I just showed you. And every one of them are written there too. You want to know more about post hoc test? All right. The one we use is this one, HSD, studentized range statistics. More about. So this is our research question for tonight. And we're going to do that. Then we're going to do a statistic, SPSS, and then we're going to do some calculation. We're going to do some um, again, non-parametric test equal to this test, because this, just like the t-test, is non-parametric test. And in non-parametric tests, you keep in mind you have to have at least 30 participants in each group. So if you really wanted to do this, you have to have 30, 30, 30, 30. That's 120 participants. So we need to have 120 scores and numbers. So that makes things very complicated, and it might create error, and that way we lose connectivities. It's better to stick with the fewer numbers so we understand the concepts. Once we learn that and we realize that if you really want to conduct this research, you need to find out what is the non-parametric test design and is equal to independent measure t-test, which is called KK-Wallace or Kruskov-Wallace. We talk about it in a second. So it says the data that I'm going to show you right here, this data that I just showed you, 4 different groups and totals for each group, SS for each group, and mean for each group, and then, all right, the same data I showed you. People satisfaction, which is in red, DV, that's a question, measure on a scale of 1 to 7. On viewing a big screen TV, so that's our IV, and it has 4 different levels from different views, from 9 feet, 12 feet, 15 feet. So every person watched 30 minutes of TV, and then we give them a questionnaire on a scale of 1 to 7. 1 be very bad, 7 will be, actually that should be 0 to 7. 0 to 7, 0 very bad, definitely need to move, and 7 is excellent. And then says, what is the purpose of ANOVA and all that? T's are total and all that. So again, 0, because we have 0, so that is very bad. Here's our data, and we test our hypothesis. So we wanted to know if there's significant difference between the groups, between the treatments. In other words, if people have any preference watching big screen TV. Step 1, the note says, even Steven, no difference, as usual. Step 2, the researcher hypothesis or alternative, we say at least one treatment is different than others. So we have 4 treatments, and D, the effect size. If it's a big difference, you're going to see big distances between them, large distance. But there's no differences. They're all going to come together, and you see only one. They all have the same mean. So that's how you visualize it and you see it. So this is our critical value for F. It's on 2 pages, one for alpha of 0.05, 692, and then for alpha of 0.01, it's on the next page, 693, if you used the text that I showed you in the beginning of the semester. If you use any other textbook, just look for F value, that's ANOVA. And in order to find that, again, you have column and you have rows. Columns, it says DF error terms, which is DF within. And rows are DF between with B. So let's go and calculate our DF between and within, find out what is our critical value is. The next one, this one is, they ask for alpha of 0.01, as you can see. But this one is specifically said 0.05. And then the next one on page 699 is for that critical value for studentized range statistics. And we get to this too. So once again, in step 2, we need to know our critical region, where we start. As you can see, it's not normal distribution, it's positively. So that red will be the critical region. So let's find out what it is. What's the number that would for the cut point? This is the formula we just talked about. So let's find out what is the DF between and within. Between, okay, on top is K minus 1, very simple. We have 4 group, take away 1 is 3. That's DF between, in red, between. And within is N minus K. That means the total number of participants are 20 minus K, which is 4, group is 16. So 4 is between, go back, 4 is between, our numerator is 4, the row. It says DF between is 4, and you go down all the way to 16, which is our DF error or denominator. And you will see that where that red line is. I'm sorry. Yeah. Degrees of freedom. Okay, it's 3. Sorry. K is 4. So DF between is K minus 1. So that's 3. And you can, so look at the blue line. The blue line. Look at the row number 3. Column, go down, go to left, you see 16. That's our DF error or DF within. And right there, I had a blue ink. It says 3.24. 3.24 is our critical region. That means right there when that cut point should be 3.24. And that's exactly what I did here. We started our, okay, remember, you start from 0 and go all the way to infinite. 3.24, right when the cut point is, highlighted in blue. That's our step 2. Find out your critical region. Step 3, calculate the F, calculate your ANOVA. It's just like calculate the T. It's the same steps, because but this one, takes more time. So, and that's what we're going to do. We need first thing first, MS between, all right, on top, red, the red part. MS between is SS between divided by DF between. So SS between, that's the formula. Sum of T squared over N minus G squared over N. So here T means total, and your number for total are 5, 10, 25, and 20. So you square them, and you can see square of the first one, 5 is 25, 10 is 100, and then the next one, 15, 625, and 20 is 400. And denominator N is same for every one of them, is 5, 5, 5, 5, 5. That's one bracket minus G squared. G is 60. You square it, is 3600 divided by N, which is total number of participants, 3600 divided by 20. And you subtract those two brackets, and that would be 230 minus 180 will be 50. So 50 is our SS between. and SS between on top it says 50, and DF between that we know is K minus 1. 4 minus 1 is 3. 50 divided by 3 is 16.66. So that 16.66, it goes right there on top of the F formula, ANOVA formula, 16.66. The bottom one, MS within, go to green now. MS within is SS within divided by DF within. SS within is sum of SS. Look on your data on the top right and add up all the SS. SS1 is 8, then 10, and then 6. 8 plus 8 plus 10 plus 6 is 32. Okay, so that's 32, and DF within we said is 16, n minus k. Or okay, because there are 5 people in each group, so n minus 1 for each group will be 5 minus 1, 5 minus 1, which is 4, 4, 4, 4, 4, 16, either way. So 32 divided by 16 is 2. Go on top, plug it into MS within. 16.66 divided by 2 is 8.3. That is our calculated F. Just like when we did the same thing with T and Z. That was calculated. Okay, so our calculated ANOVA is that. Our critical value for ANOVA is 3.24. We looked it up. So what does that mean? We're going to find out on step 4 if that value, 8.33, is greater than 3.24. Yes, it is. And you can see that blue dot right there inside the rejection zone. And that tells us our decision is to reject the node. Everything else on the right side, bottom right, are they're important, but we already talked about them. Okay, again, how to calculate eta square. Now you just get a SS. We already know what SS between is, which is 50, and SS total. If you add up both SS between is 50, SS total is 32, is 82. So 50 divided by SS total, which is 82, gives us 0.60. And that convert into percentage, which is 60%. That means there's 60%, if we reject the no, there's 60% chance that, yes, people have a preference to watch big screen TV from a specific distance. DF total, n minus 1, the 20, again, we talked about that. And if you want to calculate SS total by itself from scratch, sum of x squared minus g squared over n. So that's all formula. But we're not finished, because we still have to decide now that we reject the node, and we decided that there are differences between these group or preferences or distances. Where are they? Are they difference between group 1 and 2, 1 and 3? So if you notice right in the middle of the, let me just make this larger. Right there in the middle, when it says F is always positive value, and then you see the treatments or groups. We have treatment 1 and 2, which is 9 feet and 12 feet. Okay, we have 4 treatment. K is 4. Let's call them group 1, group 2, group 3, group 4. So group 1 and 2, that is treatment 9 and 12. 1 and 3, that's 9 and 15. Okay, so we write all treatment combination. There is 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4, right in the middle. We want to know where the differences are. Perform post hoc test. The one we're going to select is Tukey. Tukey, honestly significant difference test. And that's the formula. HST, honestly significant difference, is Q times square root of MS within treatment divided by N. N is same for all groups, which is 5. So we need to find out our Q value. And okay, so we go to another critical value. What is our critical value for Q? Right there, we need to know DF error is 16, okay? And then K, not DF between, but K. That right there, it says R, which is number of steps, is K. This time, R row represents K, number of treatment. Now we have 4 treatments. So number 4, go down all the way to 16. And now you see the red line across from 16, which is our DF error term, or DF within. And the number is 4.05. We need that number, 4.05, and to plug it in here in the middle of this distribution. So it's okay, Q, which student times range statistics. The value of it is 4.05 times, that's 4.05 times the square root of MS within treatment, which we already calculated. MS within, green on the left side, is 2. And N is 5 for all of them. You solve this problem. Okay, 2 divided by 5, square root of that is 0.63 times, again, 4.05 times 0.63 is 2.55. So HST, Tukey, give us a number. You can see I underline it, double line, 2.55. We need that number because that number is going to tell us where the significant differences are. If you go back on top, when I put the numbers 1 and 2, 1 and 3, what you do, those are mean for treatment 1 and 2, treatment 2. The difference between the two mean. So the difference between treatment 1 and 2, look at the mean. Mean for treatment 1 is 1 and for treatment 2 is 2. So the difference is 1 point. Now the question is there a significant difference? There's 1 point difference. No, because you compare that number with Tukey, HSD, which is 2.55. If that number is greater than 2.55, yes, it's significant. Since it's less than 2.55, it's not significant. So same thing we do with the others. Group 1 and 3. 1 and 3 mean is 1. And then group 3 mean is 5. The difference is 4 point. That number is greater than 2.45, 2.55. So we circle it, meaning that's significance. 1 and 4. 1 is 1, 4 is 4. The difference is 3 point. That is greater than 2.5 is significant. Another red circle. 2 and 3. Group 2, mean is 2 and 3 is 5. The difference is 3 point. That's also greater. Okay, circled. And then 2 and 4, group 2 and 4, which is mean is 2 and 4 is 4. The difference is 2 point. That's less than 2.55. No significant difference. Last one, 3 and 4, which is 5 and 4. The difference is 1 point. That's not significant. So those are the significance, and that's the now we know, that's the purpose of using post hoc tests to tell us where the differences are. Now you have it. We're going to do all this now using SPSS. And you're going to appreciate the SPSS. I'm going to do all this within just a second. Okay? If you follow this link, it also helps you to do the calculation. That's the Tukey. So let's do the SPSS. Once again, you turn on your computer, okay? And you go to variable view, always the same. Name your variable or distance. And then we have satisfaction. So you click on data view at the bottom left. And then you will have 2 set of column. Distance, we have 4 distances. Okay, 5 people in each. So you write 1, 1, 1, 1, 1, 5 times. That means 5 people, person 1 to 5 or group 1. And then 2, 2, 2, 2, 5 times 3, 3, and 5, and then 4. So look at the first column in blue. We have 20 people, and those are our 4 groups, and those are our scores that I showed you, the raw score I showed you. You go to analyze, same thing we've been doing. Click on compare means, and now select one-way ANOVA. And bam. Now you got it. You here in that rectangular, you see the satisfaction and distance. Move the satisfaction, that right there. They were both here, okay? You see satisfaction, move it from here to here by just highlight it and click on the arrow. And the distance here, click on it, drag and paste it, and bring it here, or highlight it, click on arrow. Click on distance. And then it says factor. Factor means IV, and then dependent is DV. That's what they are. So your dependent variable, like we said, is distances. Your dependent variable is satisfaction, which you're measuring. Satisfaction on a scale of 1 to 7. That's the definition for DV, is the variable we measure. And factor is IV, independent variable, is the variable we manipulate. In this case, we have 4 groups. We got manipulated, like these guys, you go in group 1, you go in group 2, group 3, group 5. And SPSS does more than what we ask. As you can see, if you click on post hoc, you see all of these are post hoc tests. And they have a strange name like LSD, Shafay, Bonferroni, and all that. But click on Tukey, like the one I did, check it. And then in terms of alpha, is automatically should be on 0.05, but you can change it if the question says change it to 0.01, then just write 0.01. Then click continue. Keep in mind, it's not too late to learn these SPSS. And there are help at Albicio that they can tutor you with this. It's a matter of you and your time and really wanted to do this and get a better grade. That's your choice. Um, because again, that is the major component of your course you're taking, especially for advanced stats, which the formula are going to be like this, and it's going to keep even bigger, getting bigger. What does that mean? It means that we probably not going to do any more manual calculation like we've been doing. We just have to use SPSS because it's the calculation have become humongous. And that's why we use SPSS to do it for us. We have the technology. Um, so you click continue, you click OK, and that's it. And once again, ANOVA, let me just slideshow. It's customary to create table like this for ANOVA, and the way you read it is first column, you have between, within, total. You add up between and within, you get total. So you get SS, the second column is SS. Okay, so SS between is 50. Same thing we did. And then SS within, go to left, you see 32. SS total, 82. Also, degrees of freedom between is 3. Within is 16. Total, add them up. So for your final, you see a table like this, and I ask you, for example, what is your DF within here? Well, degrees of freedom within group is, you can see that DF is degrees of freedom, and you see within group, they meet each other when it says 16. Or mean square, MS between. What is the MS within? It's 2. We calculate that. And F, calculated ANOVA, is 8. Now, big question is, did we reject the null according to this? Alpha 0.05. Yes, because the p-value, right, insignificant, in a circle, red, that's probability, is less than 0.05. We said that. It's always the same. If p-value is less than alpha, we reject. Again, even if it was 0.01, we reject because this is 0.001, 0.001. And so that's how you read that. Again, keep in mind for final you will have something like that, and you have to be able to interpret that. And then in terms of post hoc tests, SPSS by default repeat itself. And same thing we did, except like you can see that group 1, 2, 3, 4, right? In the first row, no, the second row, when it says 1 and 2, 1 and 3, 1 and 4, and the one that you see little asterisk are significance. And then repeating itself because you can see 1 and 3 is -4, that's that 4-point difference and significant. And then you go down to 3 and 3 and 1, 1 and 3, 3 and 4, they're the same thing. It's just 4 points. It's 4-point difference, whether it's positive or negative. That's one way to read this and find out which are the difference with significant. And it says, another way is to look at where it says sig, S-I-G, significant. If any of those numbers less than 0.05, like again 1 and 3 is 0.002, those are significant. 0.019, that's less than 0.05. So you can go there and check them out. So the reality is if we have this with 5 people in each group, you cannot perform ANOVA. You need to know what is the Non-parametric tests substitute for one-way independent measure ANOVA for this. There's one, and it's called Kruskal-Wallis test by ranks, or KK-Wallis for short, which is just a chi-square test of goodness of fit. We will talk more about this in advanced statistics. What is chi-square, which is the best non-parametric test. The only non-parametric test that we're going to manually calculate will be chi-square, not chi, but chi. And the way we do it, once again, here's the steps, you know, step by steps, how to do it. But simply, you go back to your input, the data that we put in, as you can see them. And this time you go to Analyze, you go to Non-Parametrics, Legacy Dialog, and K-Independent Sample. K-Independent Sample, and same thing we did, you move your dependent variable, which is satisfaction, to top, and independent variable to the bottom. And then you can click right there when there are two question marks, and then that another window opens. It says minimum, maximum. That's number of your groups or treatments. Maximum, you have 4 treatments, 4 groups, and the minimum is just 1 group. And then the last thing is make sure you select Kruskal-Wallis, KK-Wallis. Yeah. And there you are. Now, again, we know that by default, alpha is 0.05, and the number that you see at the bottom table is 0.008. That is less than 0.05. So yes, we reject the note if we had to do a KK-Wallis or Kruskal-Wallis. And it has other information for you, again, the mean, standard deviation, and all that. So you can put in your research paper or dissertation. The questions are very simple, and you do them, send them to me, you get extra point, would help your grades. But again, they're not going to be substitute for your SPSS assignment. And again, just read what the question asking you. Say, what is degree of freedom between treatment? DF between N minus K. So 3 treatment, capital N is 30, and minus K is 3. 30 minus 3 is that simple. If you understand the concept, these are really easy if you want to do it. Research study for treatment, that is case 4, with N5. So 5 times 4 is 20. Capital N, total participant, is 20. SS value for the 4 treatments are bam, 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 okay? Then, what is the variance? The analysis of variance would produce SS within. We want to know what SS within is. You look at your formula page or slide, and SS within is sum of SS. Add them up. 10 plus 20 plus 30 plus 40. That's the answer. So again, your last quiz will be just like that. It deals with those. And then this also will be in your final exam. So once again, good luck with your final exam. Go back and look if you're missing any of those quizzes, all the way from quiz 1 until, which was midterm. Look at the midterm quizzes, look at the final quizzes and make sure you took all of them. And take the final exam. You have 2 weeks to take the final exam now. And then again, is your last chance to do the SPSS. Get a help if you want a better grade than B. A better grade than B. I have to see some SPSS. Again, good luck with all of your classes and final exams. Have a great Thanksgiving and holidays. And hopefully I will see you soon next semester or summer, and we'll continue with advanced stats. And please don't hesitate if you have any question, just email me and I will respond within 24 hours with any question or concern. Once again, have a great holidays, and it was great having you as a student or BU professor. Bye-bye.